Hey everybody, let's finish up this unit on trig formulas, identities, and all of that. Our last part of this is going to involve solving trig equations. Now, identities are true for any value of the variable. So it doesn't matter whether you have x, t, theta, n, whatever you're dealing with there. But when you solve an equation, you're trying to find the value when possible, that makes the equation true. Identities are true for anything at all, but equations are only true for specific values. Most are not identities. There are some equations that are true for every value, therefore an identity. But you can always check and see if something's a solution. For example, let's look at this first one. Which of the following are solutions of the sine of x equals -1/2? Well, think about, that's an equation. Think about what we've done, and we've actually answered this type of equation before. Knowing the unit circle is going to be a big part of this. Notice that the sign is negative here. Where is sign negative? Sign is your y values, so if you think about your unit circle, your sign is negative in quadrants 3 and 4. So again, thinking about the unit circle, this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi. Pi over 6 is in quadrant 1. That's a positive sign. That won't work. 5 pi over 6 isn't quite to pi because pi is 6 pi over 6. 5 pi over 6 isn't quite there. That's in quadrant 2. Won't work. So I automatically eliminated 2 of them. Now, let's look at these guys. What about 7 pi over 6 and 11 pi over 6? Well, let's check. The sign of 7 pi over 6. You are in quadrant 3. Therefore, you are negative. So we know this is negative. And remember, your pi over 6 angles, you have a terminating point where the x value is square root of 3 over 2 and the y value is 1/2. Your y value represents the sine of the angle. So at any pi over multiple of pi over 6, any pi over 6 angle, the sine is going to involve a 1/2. We're in quadrant 3, so it's negative, so that is a -1/2. C works. If we look at the sine of 11 pi over 6, again, 11 pi over 6 is almost 2 pi. That's quadrant 4. It's negative, so we know it's going to be negative. And it's one of the pi over 6 angles after being simplified. So that's going to be a -1/2. It checks out. So parts C and D work. Know the unit circle. You had to know this from day one. The more you know your unit circle, the quicker you're going to notice what those answers are and which ones work. So that's why whenever we have a test or something, I always give you a blank unit circle that you can fill out because you'll be able to deal with what's going on a lot more quickly, okay? Let's go ahead and look at equations in general. The goal, whenever you're trying to solve an equation, is basically 3 steps, sometimes just 2, kind of depends on what's going on. Identify the value of the trig function. Basically, what you're looking at here is you want to isolate your trig function, okay? So, if you have sine involved, get sine of x by itself. If you have tangent involved, get tangent of x or tangent of theta by itself. Whatever your trig function is that's involved, get it alone on one side. Sometimes you might have more than one trig function, and you would have to go through and use your identities or your formulas to get it in a form that only has one. Sometimes what is inside your trig function, the angle, might not just be a variable, it might be an expression itself. We'll look at those as we go through. Your second step is solve for the expression that's inside the trig function. Solve for the angle. What angle makes that trig function true? We just did that when we talked about sine of x equaling -1/2. The angles that made that true on one revolution of the unit circle were 7 pi over 6 and 11 pi over 6. Okay? That represents an angle. What angles make it true? And the last step, you may be asked to find a general solution, or a problem might just say solve without having an interval or anything that you're wanting to deal with. Our trig functions are periodic. They repeat. You can go around the unit circle forever, right? So there are infinite angles that make equations true because we keep hitting coterminal angles as we go. Because of that, sometimes we want to write it as the general solution that represents every single one of those angles. We're going to do quite a few examples. Keep these steps in mind. Get your trig function alone, solve for the angle itself, and then get your general solution. Okay? Let's start looking at some of our examples. First of all, we want to solve the cosine of theta equals the square root of 2 over 2. First step, isolate that trig function. Well, guess what? Cosine of theta is already alone on one side. We've done it. We have that. First step's done. What angles make the equation true? Think about your unit circle. Where on the unit circle is the cosine of the angle equal to a positive root 2 over 2? If you need to, you can think about the unit circle itself. Okay. Well, at pi over 4, that's the ordered pair, square root of 2 over 2, square root of 2 over 2. Cosine of the angle is your x coordinate. So right there, okay? And cosine is positive in quadrants 1 and 4. That's where you have a positive x coordinate. The angle that corresponds to this in quadrant 4 is 7 pi over 4. That has the ordered pair root 2 over 2, negative root 2 over 2. Notice both of these guys have a positive square root of 2 over 2 for the x. Cosine's negative over here, so there's no angle in quadrants 2 or 3 that'll work. So the angles that make the equation true are pi over 4 and 7 pi over 4. Now, the angle is the part that is inside your cosine function. That's the theta. So that's theta. Theta is equal to pi over 4 and 7 pi over 4. Now, that's on one revolution of the unit circle, okay? We want to go a little further and talk about finding all solutions of this. So when you think about that, what's happening? Any coterminal angle will result in the same x coordinate. So let's think about our first solution of pi over 4, our first angle, pi over 4. If I started at pi over 4 and I went around by one revolution, I increased it by 2 pi, okay? That's going to get me to the same place. What happens if I go around again? I could increase by another 2 pi. I could increase by another 2 pi. I could decrease by 2 pi. As long as I'm going one revolution around, I get to a solution. So I could write this as pi over 4 plus n times 2 pi where n is any integer, any nice whole number there. So lots of times you might see that written as pi over 4 plus 2n pi. Lots of times it's written that way as well. But this is the general solution for that first angle, that first case. We would do the same thing for the second angle. The second angle is 7 pi over 4. Any coterminal angle will end up at that same point, so end up with that same x value. So just like with the other, if we start at 7 pi over 4 and increase or decrease, n could be any integer, it can be positive or negative whole number. If we increase or decrease by any multiple of 2 pi, we'll end up at that same terminating point. It'll have the same x coordinate, and that would be a solution. So our general solutions for this, our final solution to this equation, is pi over 4 plus 2n pi and 7 pi over 4 plus 2n pi. Okay, as we go through and we look at those. So this is what we do when we think about our steps. You could think about what cosine looks like if you wanted to think about a graph, and we don't have to go this far here, but think about the graph of y equals the cosine of theta. Back when we did graphing, and I'll just do a quick sketch here, and I'm not doing it on any nice, there's 1, there's -1. I don't have a nice grid or anything, but think about how the graphs of cosine worked. Here's pi over 2, pi, 3 pi over 2, 2 pi, 1 revolution. Cosine started at 1, came down to here, bottomed out at -1, came back up to center, and then back up to +1. This was 1 revolution. We're looking for where these guys are square root of 2 over 2. And square root of 2 over 2 is about 0.7. So there's 0.5. Let me come back in here. 0.5. We're somewhere about right here. Okay. So notice it's hitting right here. Oh, look at that. That's halfway between. That's pi over 4. And right here. Okay. 7 pi over 4. Those are our general solutions. But what happens is we keep repeating forever in both directions. Keep repeating forever. So you're always going to hit that square root of 2 over 2 at more places. Notice right here, that's a distance of 2 pi above. Same thing, distance of 2 pi above. So every multiple of 2 pi gets you to another solution. Okay? Let's go ahead and look at another one here. All right. Solve square root of 3 cosecant of x. Let me focus that a little better. There we go. Square root of 3 cosecant of x plus 2 equals 0 on the interval 0 to 2 pi. So I'm not interested in the multiple solutions, those coterminal angles. I'm just looking at 1 revolution of the unit circle. Our first step in solving this is to isolate the trig function. Our trig function is cosecant of x. So I'm going to start with the square root of 3 cosecant of x plus 2 equals 0. And my goal is to get the cosecant of x alone. So the first thing I'm going to do is get the term with cosecant alone. Since I'm adding a 2, I'll subtract a 2 from both sides. And that gives me the square root of 3 cosecant of x. 2 minus 2 is 0, equals 0 minus 2 is a -2. And then I'm multiplying by root 3, so I'll divide both sides by square root of 3. Those cancel. So that gives me the cosecant of x equals -2 over the square root of 3. So we've isolated the trig function. Now, you can work with cosecant if you want to work with cosecant. No problem. We can work with that all the way through. But when you're talking about your reciprocal functions, your cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. Sometimes it's easier to go ahead and use the reciprocal identities. So using the fact that cosecant and sine are reciprocals of each other, this is the same thing as saying the sine of x is equal to -√3 over 2. So that's our first step. You can work with it with cosecant, but I would go ahead and always put it in the form of sine, cosine, or tangent if you can, because we recognize those a lot more. Notice that because sine is negative, sine is your y values. That means you're in quadrant 3 and quadrants 4, around 1 revolution of the unit circle. It's already helping us out here. Which angles make it true? Again, think about your unit circle. We already know we're in quadrants 3 or 4. Now, so they'll be negative. What angles have a y coordinate of square root of 3 over 2? Think about your unit circle and those, in the first quadrant, those 3 angles that we kind of focused on. The first one was pi over 6, and it has the ordered pair √3 over 2 and 1/2. The next one was pi over 4, and it has the ordered pair √2 over 2, √2 over 2. And then the last one was a pi over 3, and it had the ordered pairs 1/2 and √3 over 2. Notice that the y coordinate is square root of 3 over 2 at the over 3 angles. So down here at the angle 4 pi over 3, that's the ordered pair -1/2 and -√3 over 2. And then down here at 5 pi over 3, I know the sketches are not great there, not to scale. This is +1/2 and -√3 over 2. Our y coordinates are both -√3 over 2. So our angles are 4 pi over 3 and 5 pi over 3. For this problem, what represented our angle? Our angle is what was inside the function. Our angle is represented by x, okay? So that means x is equal to 4 pi over 3 and 5 pi over 3 on the interval from 0 to 2 pi, 1 revolution of the unit circle. There's our answers. Now, if it just said solve, if it didn't give us that specific interval, if it just said solve or asked for the general solution, whichever way the wording is there, then we would need to go ahead and do the coterminal angles just like we did back in that last example. Okay? Let's look at another. We're going to do bunches of examples today. Solve 2 times the cosine of 2x minus square root of 3 equals 0 on the interval 0 to 2 pi. So again, we're looking at 1 revolution of the unit circle. So we don't need the general solution. We just need specific values. My first step is to isolate the trig function. So let's look at this. We have 2 cosine of 2x minus √3 equals 0. We need to get down to cosine of x, cosine of 2x, excuse me, being by itself. So first thing, I'm going to get that term alone. I'm going to add a square root of 3 to both sides. So that tells me that I end up with 2 cosine of 2x equals negative root 3 plus root 3 cancel. 0 plus square root of 3 is square root of 3. Then we're multiplying by 2. So I'm going to divide both sides by 2. Those cancel. So that's going to give me cosine of 2x equals square root of 3 over 2. Very similar to the last problem we did, but that's our first step. It is in the form of a cosine. So we're talking about our x coordinates. Now, what's different about this one than the others that we looked at so far? Notice, look inside the trig function. Our angle, the part that's inside our trig function, is represented by a 2x, not just the variable as it had been in others. That's going to change things a little bit. Be careful, okay? The angle is not the variable. It's an expression involving the variable. That's going to make a difference. Because in our solution, when we talk about our solution here, what's going on over 2 pi, our solutions are going to be what is x equal to, not what's the angle equal to. And we want the x to be in the interval. So we want x values over 0 to 2 pi. So what's that mean for the angle? The angle is 2x. So if x is between 0 and 2 pi, that means our angle, 2x, must be between, well, to get a 2x, I would have had to multiply by 2. When you have an inequality and you multiply one part, multiply all the parts. What that means is we want to find the angles on the interval 0 to 4 pi, where the cosine of the angle is equal to root 3 over 2. The cosine of 2x is equal to root 3 over 2. Not just 0 to 2 pi. That's the difference with this one. We're actually going around 2 revolutions of the unit circle for this, okay? So let's look at what we have going on here. Let's think about 1 revolution. So think about your unit circle. Cosine is positive. We want cosine of the angle to be root 3 over 2. That's positive. Cosine's positive in quadrants 1 and quadrant 4. Cosine's root 3 over 2 at the pi over 6 angle, because that's square root of 3 over 2 and 1/2. And at the 11 pi over 6 angle, okay? So what's that mean for us here? That means that our angle, which is 2x, can be pi over 6. It could also be 11 pi over 6. But that's just 1 revolution. That gets you up to 2 pi. We need a second revolution to get us to 4 pi. Okay? So, for the angle pi over 6, if we go 1 revolution around that coterminal angle, 2 pi is the same as 12 pi over 6. That would be 13 pi over 6. Excuse me, my paper's getting all crinkly here. Okay. And do the same thing for the 11 pi over 6 angle. 11 pi over 6, if we increase it by 2 pi, 1 revolution, we get 11 pi over 6 plus 12 pi over 6, and that's 23 pi over 6. Notice all of these values are within the interval 0 to 4 pi. 4 pi with a denominator of 6 would be 24 pi over 6. So we're just shy of that second revolution. We have 4 solutions to this guy, okay? But the question is, we want to solve the equation. That means we want to solve for the variable. We know that 2x, I'm going to move this paper up. So we now know that 2x is equal to pi over 6. 2x can be 11 pi over 6. 2x can be 13 pi over 6, or 2x can be 23 pi over 6. If you want to solve an equation, 2x equals pi over 6, we'd have to divide both sides by 2. I'm just going to do this for the 1. Pi over 6 divided by 2 is pi over 6 times 1/2. That's pi over 12. So when we divide pi over 6 by 2, it actually multiplies the denominator by 2. That's pi over 12. If we did that for each one of these, we're going to end up with pi over 12 from the first one, 11 pi over 12 for the second one. Divide that one by 2, you'll get 13 pi over 12. And divide the last one by 2, you'll get 23 pi over 12. These are our solutions. Notice all of these values are between, that's on the interval 0 to 2 pi. Because with a denominator of 12, 2 pi is 24 pi over 12. 23 pi over 12 is just shy of that. So we have all of our solutions over the interval 0 to 2 pi. You have to adjust for that special case. Okay? Look at the next one. Solve tangent of x over 2 equals 1 on the interval negative pi to pi. Now, when you look at this, the given interval, you don't want your general solutions when you have a given interval. Isolate the trig function. We already have the tangent of x over 2 is equal to 1. It's isolated. We're done. We didn't have to do any work for that one. And just like the last one, we have to be careful. Our angle is x over 2. Our angle is x over 2. We want to solve for x over the interval negative pi over pi. So in the second step where we solve for the angle, we need to know if x is in that interval negative pi to pi, what's that mean about our angle, which is pi over 2? Well, to go from x over 2, I'm jumping to those pi's there, x over 2. So to go from x to x over 2, I'd have to divide by 2. Whatever you do to one part, do to all 3 parts. So that's negative pi over 2 to pi over 2. So what we want to do first is we want to solve for the angle over the interval negative pi over 2 to pi over 2. Now we're talking about tangent. Tangent of negative pi over 2 and pi over 2 are both undefined, so it can't be either of those, but something in between. Let's look at what's going on. If we look at the unit circle, okay, in the first quadrant, it's that angle pi over 4 where your x and y value are the same. So your tangent of pi over 4 is root 2 over 2 over itself, which is 1. It's that pi over 4 angle in quadrant 1 that makes that happen. But what's happening? We're only wanting to go from negative pi over 2 to pi over 2. Negative pi over 2 is down here. Pi over 2 is up here. So we're only interested in this portion, quadrants 4 and quadrant 1. Tangent is positive in quadrant 1, negative in quadrant 4. Our equation wants to know where the tangent of the angle is positive 1. So we don't have any angles down here that'll work, okay? And there's actually only one angle in quadrant 1 that'll work. That's pi over 4. So we only have one solution for this one, and that is the angle is pi over 4. That's the only solution that'll work for the angle. Now, what's that mean? The angle is x over 2. So that means x over 2 is equal to pi over 4. Let's solve this for x. So I'm going to multiply both sides by 2. That way, those cancel, and we have x. Pi over 4 times 2 is pi over 2. That is in the interval negative pi to pi. We have one solution. X is pi over 2, and that's it for that one, okay? Remember, if you're having some questions on these as you go, jot down your question. Shoot me a message if you want some more explanation. Just like with our identities and functions, it's going to be practice, 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 okay? Let's look at more. Look at this guy. This one's going to be weird. This one's going to be a lot stranger than the ones we've looked at so far. Solve. 2 times the sine of x plus cosine of 2x equals negative 0.7. There are a few heads ups on this one. Look at this. We have both sine and cosine. Not only that, the angles are different. We have an x, we have a 2x. Now we could use our double angle formula for cosine and get it in the form of sine and get just sine involved. That would be fine. But another issue with this one is negative 0.7, the decimal. Does it even feel possible that we're going to end up with one of our nice values? Think about the nice values that we find using our unit circle. They involve 1/2, root 2 over 2s, root 3 over 2s. Those are all nice values when we think about those. Ones, zeros. With a negative 0.7, kind of unlikely that we're going to end up with those. So every once in a while, you're going to come across one that the best we can do is find an estimate or the approximate value with our calculator. So this won't be a lot, but I am going to keep it in radians. So a few things. I want to make sure my calculator is in radian mode, not degrees, okay? And I'm going to go through my steps, but what I'm going to do is I'm going to go to the y equals button in the upper left, and beside my y1, I'm going to type in that left side of the expression. I'm going to type in 2 sine of x plus cosine of 2x. Beside y2, I'm going to type in the right side of the equation, negative 0.7, and I want to find where these two intersect, find the intersection of the values. So let me mimic that here. We have y equals, okay? Clear it, in just a second. This is not focusing very well. Let me see if I can get it to get clearer. I might have to move this down and really focus in. Bear with me. Trying to get it where you can see it. There we go. All right. So my y1, I'm going to type 2 sine of x. We'll close off that parenthesis. Plus cosine 2x. Close off that parenthesis. That's the left side. For my y2, I'm going to type the right side, which was negative 0.7 or negative 0.7. Now I'm going to go ahead and look. I'm interested in the interval from 0 to 2 pi. So I'm going to go to this window setting right here. And I'm going to make sure I'm only interested in the x values being from 0 to 2 pi. Okay. And I'm going to hit graph here. Now notice it's really tiny, right? As soon as this finishes, I'm going to mess with this window setting just a little bit more. And in your notes, you have a graph of this blown up as well. Let's look at this. It's still doing the twirly. There we go. So I'm really going to kind of focus in a little more. Let's look at that. This is our first side, the one that involves sine and cosine. And then in red, I'm going to have the right side. There we go. Notice over that interval, we have 2 solutions. We have 2 intersection points right there and over here too. So to get your point of intersection, I'm going to do it here, but I'll write down steps for you as well. You're going to want to use this calculate menu here. Second trace will give you the calculate menu. You want to know where they intersect. So I want that 5th choice that says intersect. You can use your left and right arrows to move around. I'm just going to move close to one. It doesn't have to be right on it. I'm going to hit enter 3 times. Now you can see it better on your notes, but that point of intersection is 3.7225. And then I'm going to jot that down. We do it again. I'm going to move the cursor closer to the other point of intersection. I'm moving to the right. Hit enter 3 times. And we get a 5.7022, so on. That's how you can use your calculator to do it. Now, bear with me while I adjust the camera again. Okay, so what steps did I take there? I set my window settings up. You can go back and watch the video on how I did that. And then I graphed it. Then I went second trace, and I did the 5th choice, which said intersect. And I moved my cursors and found my points. Our values were 3.7225 and it went on, and 5.7022 and it went on. Round to however many decimals you're asked to round. Lots of times we'll say 2 or 3. So if we went 3 decimal places, these would be our solutions, approximate solutions. But we had 2 solutions on that interval. So we can use our calculator. It'll be rare that we have to, but we can use our calculator as we go through. Okay? Almost done, but a couple more examples to look at. Algebra. Sometimes, and let me get this back where it was. There we go. Sometimes we have to pull algebra into it, okay? When we look at these, and if you need to ever take a break from the video, you can always pause it, come back later and pick up where you left off, okay? This is an extra long video here. Some equations can be solved with the help of factoring. Think about how you factored back in algebra. We always looked at, do you have a greatest common factor you can pull out first? Binomials, do you have a difference of squares or even a sum or a difference of cubes? If so, binomials can be factored. Trinomials, well, lots of times we use trial and error. Some people call it guess and check. Some people use a C method. Some people use an area like a model, a box method. That's fine. For terms, try grouping. But think about your steps of factoring that you used, and you can still factor. And when you want to solve by factoring, you get 0 on one side. You factor the non-zero side, and you set each factor equal to 0 and solve. Some of our problems can be solved in this method. Let's look at this next example. Find solutions to the equation 2 sine squared x cosine x minus cosine of x equals 0. Well, notice, if we can use factoring, we need 0 on one side. We have it, okay? Notice that in the subtraction, we have a common factor. We have a cosine of x involved in both terms. So I have a greatest common factor of the cosine of x, and I'm going to factor it out. So I have the cosine of x times. If I take the cosine of x out of the first term, I'm left with 2 sine squared of x minus, and remember with addition and subtraction, you have to have something on each side of it. I factored the cosine of x out, so that just leaves me with a 1. Because cosine of x times 1 is cosine of x. So that product is equal to 0. So there's our first step. And when you're solving by factoring, what you do is you take each factor and set it equal to 0. So either cosine of x is equal to 0 or 2 sine squared x minus 1 is equal to 0. So we have two cases here that are going to give us solutions. And what we're going to do is look at each case, okay? And we're going to follow the process that we did in the last problem. In all of our examples so far, what do we need to do? Get the trig function alone, solve for the angle. This one didn't give us a specific interval, so we want our general solution. We're going to do that for each case. So first case, when is the cosine of x going to be 0? Think about your unit circle. Cosine of x is your x coordinate at the points. We have a point here where you have the point 0, 1, a point here where you have the point 0, -1. This is at pi over 2 and 3 pi over 2. In both of those cases, our cosine is 0. So our angles in one revolution are pi over 2 and 3 pi over 2. That is, our angle is x. So unlike the last couple of examples, it is our x value. So our x value is pi over 2 and 3 pi over 2. In one revolution, those are our solutions. So we got the trig function alone. We solved for the angle. Now we need our general solution, which is something that we were looking at where we look at revolutions. Notice something special about these. From pi over 2 up to 3 pi over 2, that's an increase of half of a circle or half of a rotation. That's an increase of pi. And if I go from 3 pi over 2 back up here, that's an increase of half of a circle or a revolution pi. We have a same amount between the two. So what I could actually do is take pi over 2 and increase it by any multiple of pi. And that's going to get me to all of my solutions, okay? Because if I start up here and add pi, that gets me to the 3 pi over 2. If I add pi, that gets me to the next coterminal angle at pi over 2. Add pi, that gets me back to the coterminal angle here. It's going to keep bringing me to those same terminating points. So I didn't have to write 2 general solutions like I did in some of our earlier problems, because I had an equal distance between my solutions. I could condense it into one case. That's case 1, okay? We're also going to need to deal with it for this case here, case 2. So for the second case, we have 2 sine squared x minus 1 equals 0. What's our first step when solving? Get the trig function alone. So this would be the same as 2 sine squared x equals 1 if you add a 1 to both sides. Divide by 2, and you'll get sine squared x equals 1/2. But we want to solve for sine. So to undo the square, we take the square root. Sine x would be positive or negative the square root of 1/2. That's positive or negative 1 over square root of 2. And if you rationalize it, that gives you a positive or negative square root of 2 over 2. The reason we need the positive or negative, think back to algebra days. What happens if you square negative? You get a positive answer. We'd still get a positive 1/2. What happens if you square positive? You get a positive answer. That number that's being squared can be positive or negative. So there's our first part there. Think about your unit circle on this guy. Where is sine, or your y value, root 2 over 2? Well, in the first quadrant, that's happening at pi over 4. Positive root 2 over 2. In the second quadrant, that's happening at 3 pi over 4. And you don't have to do the graph of the unit circle every time. Remember, if you created your unit circle at the beginning, you have all these values. I'm just wanting you to see where they fall. Okay, so this would be 5 pi over 4. This would be 7 pi over 4. It's happening at the over 4 angles. And I want positive and negative, so that fits any quadrant. So this is going to happen when our angle is any multiple pi over 4. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. That's one revolution, okay? Our angle was x. So that happens when x is equal to pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Now, general solution. Let's think the same thing. Are these equidistant from each other? If they are, we can write it in one case just like we did the last one. They actually are. Notice if you went from pi over 4 to 3 pi over 4, that difference right there, that is 1/4 of a circle, or pi over 4. That's an increase of pi over 4. From here to here, that's an increase of pi over 4. All of these are equidistant from each other. So if I start at pi over 4 and I increase it, now I can think of this a couple of ways. Notice that these coefficients are all odd, okay? Think about what's going to happen if we went up one revolution here. If I went up by 2 pi, that's 8 pi over 4. We would get a 9 pi over 4, okay? But notice what happens as I go from here to here. If I go up by, oh, let's look. It's actually not, oh, I lied. Sugar, sorry. I was so focused on pi over 4, which is this small angle. It's an increase of pi over 2. Pi over 2. It's 1/4 of a circle. That's pi over 2. Okay. Equidistance. Notice if I went up by pi over 2. Pi over 4 plus pi over 2 is pi over 4 plus 2 pi over 4. That's 3 pi over 4. Okay? So if we started with pi over 4 and we increased by multiples of pi over 2, we're going to end up at our next angles. Pi over 4 plus pi over 2 gets you here. If you go up by another pi over 2, you're going to get here. Go up by another pi over 2, you're going to get to 7 pi over 4. We go up by another pi over 2, it's going to bring us back around to a coterminal angle with the first one. And it just keeps going. So we can write our general solution has to include both of these. Okay? Our general solutions. X can be pi over 2 plus any multiple of pi, or X can be pi over 4 plus any multiple of pi over 2, where n is any integer, because you can go positive, negative, and those are your solutions. So if you're equidistant between your answers, you can consolidate. Otherwise, you can always start with each one individually. Okay? Let's look at this one. This one's going to take a little bit of work. Solve 2 cosine squared x plus 1 equals negative 3 cosine x. Well, let's look at this. We do all have cosine involved, so we have the same trig function, an angle. That's good. So let's see if factoring can help us here. I could get 0 on one side by adding 3 cosine x to both sides. And that's going to give me 2 cosine squared x. I'm going to put the 3 cosine x in the middle, plus 1 equals 0. Now, we haven't factored trig functions, but we have factored things that are trinomials. Notice the form of this guy. The form of this guy fits 2 times something squared plus 3 times that same something plus 1. It's a trinomial. There's no greatest common factor that we can bring out. So try either the AC method of factoring or trial and error. But at any rate, if you were to factor this guy, you'd get it by going 2a plus 1 times a plus 1. That's the factored form. Well, it's the same form here, except instead of an a, we have a cosine of x. So the factored form of this is actually 2 cosine of x plus 1 times cosine of x plus 1. So you can factor when it fits that form. And what do? We set each factor equal to 0. So 2 cosine of x plus 1 equals 0, or cosine of x plus 1 equals 0. This is also going to give us a couple of different cases. If I solve this, subtract 1, gives us 2 cosine of x equals negative 1, divide by 2, gives us cosine of x equals negative 1/2. And then this one, subtract 1, gives us cosine of x equals negative 1. So there are our two cases, our two situations. So we're going to do it just like we did the last one. Your first case, cosine of x equals negative 1/2. Where does that happen? When is cosine negative? Cosine of x is going to be negative in quadrants 2 and 3. Okay. When is the x coordinate a 1/2 on the unit circle? The x coordinate's 1/2 at the pi over 3 angles. So this means solutions for this one, in quadrant 2, that would be 2 pi over 3, and in quadrant 3, that would be 4 pi over 3. So those are our solutions in one revolution of the unit circle. Think of your second case. cosine of x equals -1. When's that happen? Think about your unit circle. There's the point -1, 0. That happens at the angle pi. X is equal to pi. Okay? Those are our specific solutions over one interval. What about our general solutions? What happens? Well, think about this one here. 2 pi over 3. 2 pi over 3 is right here. 4 pi over 3 is right here. They are not equidistant. Okay? This difference between the two is not the same as this difference between the two. So I'm going to have two different general solutions here. I'm going to have the one for 2 pi over 3. So 2 pi over 3, and I can go up by any full revolution. That's a multiple of 2 pi. N times 2 pi or 2n pi or 2 pi n, however you want to write it there. That'll represent all the solutions for that guy. For this one, same thing. 4 pi over 3, and we can go up any number of full revolutions. So that's a multiple of 2 pi. Over here, we just have the 1, and it can be any multiple of this. We can write this a couple of ways. So it can be pi plus any multiple of 2n. But notice, so you can write it this way. That would be fine. But notice you do have a common factor of pi. You could factor a pi out and write it as 1 plus 2n or 2n plus 1 times pi. So you have three forms of the solutions for this problem. And those are our general solutions. Now, again, if you wrote it like this, that's okay. That's true. I just simplified it down to the other version. Okay? All right. Look at this one. Now, this one, we're going to pull back an identity. Solve. Sine squared of x equals 1 minus 2 cosine x plus cosine squared x on the interval 0 to 2 pi. So it's on the interval, so I know I don't need that general solution. But what's my problem here? I have both sine of x and cosine of x. Is there a way to only use one of the two? Okay, there is. Now we have cosine in a lot of terms here, so I'm going to look at this. Remember from our Pythagorean identities, sine squared of x can be written as 1 minus cosine squared of x. So I can make this equation 1 minus cosine squared x equals 1 minus 2 cosine x plus cosine squared x. Now I have only cosine involved. That would be good. Let's see if factoring could help us out at all. We have lots going on. So I need 0 on one side. I'm going to get rid of this 1 by subtracting a 1. 1 minus 1 is 0. Whatever I do to one side, I have to do to the other. I'm going to get rid of minus cosine squared by adding cosine squared x. Those cancel and give us a 0. That gives us a 0 on the left. Whatever I do on one side, I have to do on the other. So I get 1 minus 1, that canceled out. So I have a negative 2 cosine of x plus 2 cosine squared of x. I do have a common factor. My greatest common factor is 2 times the cosine of x. So I could factor that out. You can reverse the order of these as well if you want. We'll factor 2 cosine of x out. That leaves me a negative 1 here, plus the 2's gone. Leaves me a cosine of x here. You could have written this way. They're the same. So we have two cases again. 2 cosine of x is equal to 0, or cosine x minus 1 is equal to 0. Solve. So either cosine of x is 0, or cosine of x is positive 1. Well, where's cosine of x 0? Cosine of x is 0 at pi over 2 and 3 pi over 2, because that's the ordered pair 0, 1. 0, negative 1 cosines your x coordinate. So this will happen when x is pi over 2 or 3 pi over 2. When is cosine of x 1? That happens right here. There's the point 1, 0. Now, notice in your solutions, it said on the interval 0 to 2 pi. 0 included, 2 pi not included. So, this is the angle 0 or the angle 2 pi. They're coterminal. We want the 0 version. This happens when x is equal to 0. So, on the interval 0 to 2 pi, our solutions are x equals 0, pi over 2, and 3 pi over 2. We weren't interested in the general solutions for this one. If we were, we could go through and do the same idea. Since pi over 2 and 3 pi over 2 have the same distance between them from either direction, we could have written that as one general solution. And then we would have needed a different one for the 0. Okay. All right, let's go on. Last example for this video. Sine of x equals cosecant of x. Now, we have a couple ways we can do this. First, well, one way. We know that cosecant and sine are reciprocals of each other. I know that the cosecant of x can be written as 1 over the sine of x. So what I really have here is sine of x equals 1 over the sine of x. I can get rid of fractions. I can multiply both sides by this denominator. Gives me 1 equals sine squared of x, which means the sine of x is equal to plus or minus the square root of 1, which is plus or minus 1. So, when is the sine of x equal to positive or negative 1? Sine is your y coordinate. Up here's the point 0, 1. Down here's the point 0, negative 1. So that's happening at pi over 2 and at 3 pi over 2. So x would be equal to pi over 2 or 3 pi over 2. The problem did not say over a certain interval, so I do want my general solutions. Again, notice, from pi over 2 to pi over 2, that's an increase of pi, half of a circle, or half a rotation. From 3 pi over 2 to pi over 2, it's an increase of pi. They're equidistant from each other. So I can write this as one general solution. I can take pi over 2 and increase or decrease it by any multiple of pi, and that's going to get me to all of my solutions. Okay? That's one way to do it as far as what you have going on. The other is more intuitive in nature as you go through and look at it. Since sine is equal to cosecant, and that means a number's equal to its reciprocal, the only place where you're going to have a number equal to its reciprocal is if it involves a 1, because the reciprocal of 1 is 1. Okay? So that leads us to, when is it 1 or a negative 1? And same type of idea there. Okay? But there's a way that we can go through and deal with that. So we have our solutions. Go ahead, try a bunch of these. You have your homework sections, our homework sections that deal with solving trig equations. Try them, see what questions you have, email me. I'll be happy to do more examples, more videos. Just yell as you need it done, okay? And I'll talk to you all later.